Hello and welcome to the lecture of linear algebra. In this lecture, we will talk about complex eigenvalues. So far, we have seen characteristic equations of an n by n matrix that result in real eigenvalues. But there are situations in which the characteristic equation may lead to complex eigenvalues. So if we have n by n matrix, we know that the order of this characteristic equation is n, and it will have n roots. Now these n roots may have multiple eigenvalues with algebraic multiplicities, but all the roots should be add up equals to n. Okay. Now if the roots of the characteristic equation are complex, it means the eigenvalues don't exist in the space Rn. Actually, they exist in now complex space Cn. Okay. Now, in general, as we have done previously, that determinant of a minus lambda I help us evaluate um, so help us evaluate the value of lambda. So in the case when if and only if there is a non-zero vector x, now it exists in Cn, right? So because you're talking about the complex eigenvalues such that Ax is equals to lambda x. Okay, we call now the lambda as the complex eigenvalue, and of course x is a complex eigenvector. Okay, now let's do an example to illustrate the concept of complex eigenvalues. So if we assume that the matrix A is 0 minus 1 1 0, okay, so it means if we have any vector x, let's say call x1 and x2, so in this case we will have Ax as nothing but equal to 0 minus 1 1 and 0. Okay, now if we multiply with x1 and x2, right, so it means the result will come as minus x2 and x1. So it means what happens here is that this multiplication of A has rotated the matrix. Now rotated the vector. Now x2 that was previously positive, now it's negative, and it has been replaced with x1, the position of x1, and x1 has now changed its position to x2. So it means effectively it is indicating a rotation. Now simply if you keep multiplying with the resultant vector of Ax with A again, the output here would be minus x1 and minus x2. Okay, right, so we can see here that it's a rotation going on, and again 0 minus 1 1 0. If you multiply with minus x1 and minus x2, the output will be x2 and minus x1. Similarly, if for the last time, if we do that as 0 minus 1 1 0, the answer here is x2 minus x1. The answer would be x1 and x2. So what happens is after 4, so it was shifting, this matrix A was rotating this vector by 90 degrees every time, and when it took 360 90 90 19 360, so it came back to its original position. Now, when the values of when eigenvalues are positive, the only thing that happens is the linear scaling. So it means if it was a vector x, right? So we look at the transformation which ax is equals to lambda x. So if you multiply a with x, so what happens is x actually linearly scales by lambda, because lambda is a real number. So it means this would be some way lambda x. So actually the point from by multiplication of a would only move to lambda x. But in the case of this complex of this scenario here, what we are saying here is that when you given x, if x is here and if you multiply it here, so it actually is going to rotate by 90 degrees, right? So it can go here or go here, then go here, and then come back here, right? So here, so in case when lambda is a real number, or its real values, what you have as a linear scaling. But when we'll see shortly that this matrix A has actually complex eigenvalues, and what it is doing here is it is actually rotating, it is actually performing rotation rather than scaling. Okay, so we know that the rotation here is actually uh, uh, actually needs complex eigenvalues here. We need complex eigenvalues to actually rotate this and bring it back to the same point, right? So so if I make the characteristic equation of this matrix, we know that determinant of a minus lambda I equals to 0. So if it becomes very simple that it becomes a minus lambda here and minus lambda here. So effectively the result here is lambda square plus 1 equals to 0, and I will get two eigenvalues here, which is actually iota and equals to minus iota. So lambda 1 is iota and lambda 2 is actually minus iota, right? now if we allow this a to act on the vectors in complex space, as I told you earlier, in this case of c square, so it means the eigen the eigenvector corresponding to that eigenvalue is the point where ax is equals to lambda x. So we are allowing x to exist in this complex space c square. Okay. Now, so it means what we would have is 0 1 minus 1 0 equals to this matrix x, which we don't know. Let's say x1 and x2, and it should be lambda 1 was initially iota, so we put iota here, so it will be x1 and x2. This is quite too simple matrix, 2 by 2 matrix. We can easily see that for that to be true, one of the very simple scenario in which the eigenvector corresponding to iota is nothing but equals to 1 and minus iota, right? So you will see here that iota and 1 and minus iota will yield the same thing. So it means the eigenvector corresponding to lambda 1 is actually 1 and minus iota. Similarly, you can calculate for lambda 2 is equals to minus iota, and you'll find that because it's a very simple 2 by 2 matrix, that this result is actually 1 iota and minus iota 1 iota, right? So this is correspondingly the eigenvector for lambda 2. So we can see here, first thing we can see here that lambda 1 and lambda 2 are complex conjugates, so it means they will order in pair, and also the eigenvector here is eigenvector of lambda 2 is actually a complex conjugate of eigenvector of lambda 1. Okay, now we can further demonstrate this by another example. Say if we say that a is equals to 0.5 minus 0.6, 0.75 and 1.1. What we need to do is find the eigenvalues of a and actually have to find the bases for each eigenspace, okay, as we did in the case of when the eigenvalues were real. Okay, now so we know that to find the eigenvalues, what we have to first do is to calculate the characteristic equation, which is nothing but determinant of a minus lambda I equals to 0. Okay, now when you do that, you can it's quite easy, right? You will find that you will end up with uh, something like this, right? It's given in the book, so I don't need to evaluate it over here. So you get here lambda square minus 1.6 lambda plus 1 equals 0. So it's a quadratic equation. We can solve this quadratic equation by a formula which gives us lambda 1 is equals to 0.8 plus 0.6 iota, and lambda 2 is equals to 0.8 minus 0.6 iota. We can see here again it will have two eigenvalues, and both are actually since one of them is complex, other one is its complex conjugate. Okay, so we need to find the eigenvector. So it means to find the eigenvector we have to have that a minus lambda I to the x should be equal to 0. So we put it here over here, and if we put it over here, the answer comes at 0.5, 0.6, 0.75, 1.1 minus so first one is actually 0.8 plus 0.6 iota. So first we need to find for lambda 1 is equals to 0.8 plus 0.6 iota. So it means if I multiply with lambda here, I will have this kind of matrix: 0.8 plus 0.6 iota, 0, 0, and 0.8 plus 0.6 iota. Okay, now and of course that should be multiplied by x and should be equals to 0. Okay, now if I solve this equation over here, then becomes minus this matrix addition minus 0.3 plus 0.6 iota, and minus 0.6 and 0.75 and 0.3 plus 0.6 iota. Right, now it's only a 2 by 2 matrix, so we can so what we can also do here is do the kind of row operations, but since it's a very small matrix, we can actually form equations here and substitute one variable from one of the equation into another equation, right? But so actually I can write this as 0.3 plus 0.6 iota into x1 minus 0.6 into x2 equals to 0, and then you have 0.7 x1 plus 0.3 plus 0.6 iota x2 equals to 0. Now once we have those equations, it means now I can actually solve those equations, and if I try to find out let's say x1 or x2, I can use x1 from one equation and substitute in to find out x2. Now so if I use a second equation here, which is 0.7 x1 plus 0.3 plus 0.6 iota into x2 equals to 0, right? So it means xi can be written as, if I shift it over here and this here, minus 0.4 minus 0.8 in iota into x2. Now this is from the second equation, and from the first equation we have the same. We will have the same thing again over here as well from the first equation. So you can use either of that. Actually both this equation actually represent the same thing. Okay, now it means this one is exactly actually you can say they are actually linearly dependent, right? So it means one of them can actually simply produce a 0 over here, or you can use this row to produce a 0, a complete 0 over here. Okay, so x2 then becomes the free variable, and choosing x2 is equals to 5 will give you v1 as, or the eigen corresponding minus 2, minus 4 iota and 5. And similarly, since they are complex conjugate, the eigenvalues are complex conjugate, and their vectors are also complex conjugate, so it means for lambda is equals to 0.8 minus 0.6 iota, v2 is nothing but equals to 2 plus 4 iota, sorry, minus 2 plus 4 iota and 5. Okay, so and we can easily show that, right, by simply putting av2 is equals to uh, 0.8 minus 0.6 iota times v2, right? So that will be minus 2 plus 4 iota and 5. Okay, so when you even substitute it over here, you will see that you will have exactly the same thing over here, okay, as you get from av2. So now we can use this matrix to build up our case that effectively when the matrix has complex eigenvalues, generally what it's doing is it's actually rotating the point instead of scaling the point, right? So it's scaling the eigenvector, it actually rotates the eigenvectors, right? So if we take the same matrix again which we did in previous example, which was 0.5 minus 0.6, 0.75, 1.1, and we start with some initial value x, which is x naught, which is 2 and 0, right? So it means a x naught, right, which is x1 here, is nothing but comes out to be, if you multiply that, comes out to be 1 and 1.5. Similarly, if I have x2 as a times x1, which is nothing, comes out to be minus 4 and 2.4, and similarly x3 is equals to ax2, and you will have certain values. So if I plot those over here, what you will see here that you are sitting over here at x naught, and then you went to x1 over here, and then x2 over here, and similarly you will keep on rotating over here, and you keep on that, and then you will have you will actually have an ellipse, right? So and actually an elliptical orbit, you will actually have an elliptical orbit. So uh, so what happens is basically, since this eigenvalues have both real and imaginary parts, so what it does is basically actually rotates the point, or rotates the eigenvector, rather than actually linearly scale it. Again, we can actually do another example. So if I say x is equals to 3 minus iota and 2 plus 5 iota, actually I can write this as 302 plus iota minus 1, 1 and 5. Okay, so this will help us visualize the rotation as well. So if I say x is equals to is a complex is in complex space C3 over here, so it means real of x, we know that this is real of x and this is your imaginary of x, right? And then we still have an x bar, which is a conjugate of x, is nothing but coming out as 302, and of course this will come minus iota over here, minus 1, 1 and 5, and this is 3 plus iota minus iota and 2 minus 5 iota. Now similarly, we can write the eigenvalues and eigenvectors of a real matrix, that x on Cn, as like that. So it means ax bar is nothing but ax, this one. So if a is a real matrix, a is a real matrix, so conjugate won't hurt it. So it means x is a complex vector like this one over here, and a is a real matrix. So I can actually write this as ax conjugate, and this is equal to nothing but lambda x conjugate over here, and I can write this as lambda conjugate and x conjugate. Okay, this show that when a is real and its complex values, its complex eigenvalues occur in conjugate pairs. Okay, so when a is real, its complex eigenvalues occur in conjugate pairs. Again, we can do an example to illustrate the rotation part. So if we let's say A is a matrix which is minus 0.5, minus 0.6, 0.75 and 1.1, we have already calculated the eigenvalues is 0.8 plus 0.6 iota, and lambda 2 is equals to 0.8 minus 0.6 iota, and let v1 is equals to, which we already calculated as minus 2 minus 4 iota and 5, and let's say also P be the matrix which is again as real of v1 and an imaginary of v1, okay, which is 2 minus 2 5, and actually comes out minus 4 and 0. So what I have done over here is I have this matrix A, and I have those eigenvalues over here, and for one of the eigenvalues I have this eigen vector v1. So I can calculate a matrix P which is a real of v1 and an imaginary of v1, and if there is another matrix C which is P inverse A over AP, right? So P inverse in this case will be nothing but 1 over 20, so that would be 0 here, and of course here it becomes plus, and then what you do is basically switch the position over here and change the sign, which is 4 minus 5, and then you have A as 0.75 minus 0.6, 0.75 and 1.1, sorry, this is 0.5, and again you have this P matrix which is being multiplied over here, that is minus 2 5 minus 4 0. Okay, now again this matrix is again if you look at this one over here, the output result would be C is equals to minus 0.8, minus 0.6, 0.6 and 0.8, right? So if I compare this to this matrix over here, since this A matrix, you remember in the previous example this was providing the rotation, and we got the elliptical orbit from initial starting point over here. So this is very similar to this matrix. We can see the sign over here. This is the scaling is different though, but there is a sign which indicate that there is some kind of rotation going on. So it means we can see here that C is also rotation, So what we have here is a rotation present inside this matrix A. So what we can see here is that C comes out to be 0.8 minus 0.6, 0.6 and 0.8. Now similarly I can write A as A is equals to PCP inverse. Like I have written C, then I have written A is PCP inverse, and when I multiply those up, the answer I get here is P.8 minus 0.6, 0.6 and 0.8. Now what you can see over here is this thing over here, that lambda 1 is 0.8 plus 0.6 I, right? And we are getting the same value over here as well, that this is A, right, and this is actually B. So you can think of this matrix as C is equals to, if I say this lambda 1 as A plus A minus B iota, right? So it means I can write this as A minus B, A, B and A. Okay, now again, so I can write the C matrix as A minus B, B and A, where the eigenvalue is lambda 1 is equals to A minus Bi. Okay, so we can generalize this now to say that if A is a real 2 by 2 matrix, okay, with complex eigenvalues, lambda is equals to A minus B iota, where B is not equals to 0, and an associated vector x in C square, then A can be written as PCP inverse, right? So PCP inverse, where C is a rotation matrix. Again, A is also a rotation matrix though. But anyways, you can write this matrix A and write in terms of its eigenvalues, right? So P, and where P, let's write P is nothing but the eigenvector real of V1, where V1 is the eigenvector corresponding to lambda, let's write V, and imaginary of V. So this P is a matrix that consists of the eigenvector corresponding to lambda, okay, and this is eigenvector corresponding to lambda real component and its imaginary component, okay, and C is nothing but equals to A minus B, B and A, okay. So you can write this matrix in a form which is more convenient, okay. Now generally this phenomena of rotation actually exists in, we have seen all the examples of 2 by 2 matrix, but it also equally exists in higher dimensions, and every vector in that plane is rotated into another point on the same plane. So if a point is rotated on the same plane, then we say then we say that the plane is invariant under A, or actually under the complex eigenvalues on of, of, of A. Okay, so let's summarize what we have done today. I think the discussion here was about our complex eigenvalues, and complex eigenvalues, we know that uh, um, has the same method of calculation as in the case of real eigenvalues, so that you have to find determinant of A minus lambda I equals to 0, and here lambda is the complex eigenvalues, and x is correspondingly the complex eigenvectors. Another important thing that we have learned from the examples that we covered in this topic is that these complex eigenvalues occur in pair, and correspondingly complex eigenvectors also occur in pair. It means if there is so if if one eigenvalue if there is an eigenvector corresponding to one of the complex eigenvalues for its complex conjugate of that eigenvector is an eigenvector corresponding to the complex conjugate of the first eigenvalue. So eigenvalues of A, so they actually exist in pair, and that's what you have written. When A is a real, the complex eigenvalues occur in conjugate pairs, and normally the corresponding eigenvectors are also occur in pair. Okay, another important thing that we have learned in this situation here, that if A is real and it has complex eigenvalues, it means it is not linearly scaling it is actually rotating the vector, or rotating the eigenvector. So x here, so unlike the real case where it is scaled linearly on the same line or on the same plane, here we have rotating the point on the plane, or on the line. And in fact, after a certain amount of rotations, effectively the eigenvalues, the eigen vector will actually will converge to the same point. Okay, in the examples that we consider, of course, there may be scenario in which they can, or there may be scenarios in which they cannot come back to the original point. Another important thing that we did learn today was that if A is a real 2 by 2 matrix and it has complex eigenvalues, so it means so we can take one of the eigenvalues, which is say lambda is equals to A minus bi. We can write this matrix A in terms of its eigenvalues, which is we can define a vector p which we can write as the corresponding vector to this complex eigenvalue, which is real part of this, and the imaginary part of the vector, which is corresponding to lambda. And again we can actually see that A is equals to PC P inverse. We can write this as like this, where C is nothing but composed of the eigenvalues of C. Hopefully you have understood this concept. Thank you. Allah Hafiz.